Hi everyone. In Unit 1, Alkanes and their conformations, we are going to look for the first time, for many of us, at organic compounds and the many different ways to draw them. Now, if you're taking notes, go ahead and copy these two headings. This is the first video, or probably one of the first videos for this particular unit. Okay. And in this video, we are going to discuss line drawings, how to draw organic compounds fairly quickly, and simple nomenclature. Nomenclature is just a fancy word for saying the naming of organic compounds. Alright, why don't we start out with the definition for an alkane, at least one of the definitions. For an alkane, it is a hydrocarbon that only has single bonds and, importantly, no rings. Okay. And if you can follow that definition, the molecular formula for an alkane turns out to be CnH2n plus 2. So for instance, if you have an organic molecule that has, 7 carbons, and if that molecule is an alkane, then you really should have 16 hydrogens. Okay. Now, hydrocarbon is just any molecule that only has C and H. Okay. Now, there are many compounds that fit this molecular formula, and if they all fit that molecular formula, then by definition those are alkanes. What about this idea that we should have no rings? Let's draw the Lewis structure of two very simple molecules. If you need to pause the video to catch up, go ahead and do that. Just let me draw these two molecules first. Remember that carbon, when it's neutral, should have 4 bonds, and those could be 4 single bonds, or a combination of double and single bonds, or triple and single bonds. But let's take a look at these two molecules. They both have 3 carbons. This molecule is an alkane because the formula is C3H8. But this hydrocarbon has a ring in it, and if you count up all the hydrogens, you'll notice that we are short 2 hydrogens from the 8. Okay. So when you have a ring, that molecule can never fit this formula CnH2n plus 2. Now, that's a good formula to know, but I wouldn't necessarily memorize it when you're trying to figure out the molecular formula for an organic molecule. I would just rather be able to either draw all the hydrogens or count all the hydrogens when we look at some simpler drawings. Okay. What is our first nomenclature? And we'll come back to this idea that every time you have a ring, you do lose 2 hydrogens. That's going to be actually a really cool trick when solving some of these isomer problems. Okay, but that's a bit in the future. Let us start with simple nomenclature, and this is going to be for the unbranched alkanes. And yeah, this will mainly be memorization. So if we have a molecule that looks like this, just 1 carbon, that has a special name, that's called methane. And you're going to memorize the prefix. The suffix is ane. Ane indicates that it is a, for now it indicates that it's an alkane. Later on it really means that it indicates that all the carbon-carbon bonds are single bonds. Now, this is a Lewis structure. You could shorthand this with what's called a condensed structure. Lewis structure means that you draw out all the bonds as lines, and then some professors require you to draw out all the lone pairs, but you know that that molecule has no lone pairs on any of the atoms. This is called a condensed, and there really is only one way to draw a condensed structure for methane, and it's such. Condensed meaning that you don't show any of the carbon-carbon single bonds. Well, there are exceptions. I guess you could say for condensed structures you reduce or totally eliminate the number of lines that you see. Okay, so it's a shortcut. Methane. What if we have 2 carbons? If you have 2 carbons, go ahead and practice. How many hydrogens would you expect around this 2 carbon bond? You got to add enough hydrogen so you have carbon with 4 bonds each. This is ethane, E-T-H-A-N-E. Okay, we're still keeping with the A-N-E suffix. Condensed, there are a couple ways. Some people like to do CH3, I kind of like, for the carbon on the left, I kind of like putting the hydrogens on the left side so I see the 2 carbons next to each other. Okay. And again, this is mainly preference, whether you draw it condensed this way or this way. How about 3 carbons? By the way, if you look at the molecular formula for these unbranched alkanes, you will notice that it does fit the CnH2n plus 2 rule. Okay. Let me just circle. This is our first category of nomenclature, unbranched alkanes. Next one, I think we have our 3 carbons in a row. As you probably guessed or can observe as you're trying to keep up with my drawing, that having to draw all of the bonds and all the hydrogens is kind of a pain in the, well, it's a pain. And we're going to see some shortcuts in just a bit. Propane. In terms of the condensed, maybe you could draw it like this. CH3, CH2, right? 2 hydrogens on the middle carbon, CH3. Do you notice that the condensed formula is not a molecular formula, right? The molecular formula for this is C3H8. C3H8. Okay. Now I'm going to show you something that we could use to reduce the amount of writing we have, especially for larger molecules, and it's called a line structure. The line structure for propane is this, or can be this. Alright, now for my class, you're definitely free to put dots. Okay, I think that will help some people realize that every time you have an angle, you should consider that a carbon, and every time you have something at the tip, that's also a carbon. Okay, and where's this drawing coming from? If we take a look at the, if we take a look at a model, there is propane right there. Okay. So what is line structures? Another way that you'll hear it besides line structures is line angle, drawings, structures, etc. Line angle drawings or structures. Okay. We'll take a look at your model. What are we doing to the model to make it easier to draw on paper? We're stripping off all the hydrogens that are on carbons. On the model, yeah, you're literally doing that, but in the molecule itself, the hydrogens are still there. It's just that now we have an easier way to draw it. So really what you're drawing is the carbon skeleton. Okay. Now for more complicated molecules that have oxygen, we'll see some other tricks. But for now, let's just worry about alkanes, and in particular hydrocarbons in general. I call these line drawings. Some textbooks say line angle. Some textbooks actually say bond angle. No, not bond angle. Bond line drawings. They all mean the same thing. Okay. Now, if you've been practicing with your models, well, you could also draw this molecule, propane, without breaking the model. You could twist the bond. Okay. You could twist the bond. Obviously, you could rotate it. It's still the same molecule. Still the same molecule. So you could draw propane like this. You could draw propane like that. All right. Now you're going to have to become very comfortable knowing where all the hydrogens are. And again, I like to use dots because those dots represent the black pieces on my model. Did you remember where the hydrogens were before I took them off? There are 3 hydrogens here, 2 in the middle, and 3 hydrogens on this last carbon. The way that I want you to be able to count hydrogens is sequentially. Don't say 3 plus 2 plus 3. Count like this from left to right. 1, 2, 3, 4, 5, 6, 7, 8. That's what we would have predicted. This is C3H8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. If that's not abundantly clear, make your propane carbon skeleton and put your hydrogens on each of these carbons. The models that I'm showing you here are great because, well, there are only 3 holes left on this carbon here, so that's where you're going to put the 3 hydrogens. Like that. Methane, ethane, propane. We are going to memorize for the unbranched carbons up to 10. Up to 10. We are now up to, 4 carbons. And since the molecules are getting bigger, I'm just going to draw the line structure for most of them. Butane. Meth, eth, prop, bute. Okay. Do I have butane? Well, I'm looking for my model for butane, which I don't have. No big deal. Let's count. Go ahead and pause the video. I want you to give me the molecular formula for this molecule. I have 4 carbons. 1, 2, 3, 4. C4. And count from left to right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, butane. If you have butane, why don't I just make the model real quickly? It's just 4 carbons. There's my model for butane, and what you need to be comfortable with is taking a molecule that's on paper and being able to rotate the bonds. Because if I rotate this middle bond here, I have butane that looks like that. It is still butane. So if I draw something like this to match what I see in my model, okay, approximately, this is still butane. What does that mean? We're going to consider these as identical molecules. That may be very simple now, but imagine if we have a molecule that has, 50 atoms. Would we be able to tell if 2 molecules that have the same 50 atoms, are they identical or are they rearranged differently? When I think about rearranged differently, if I take this butane and I put the carbons in this situation, you see that it's still 4 carbons. I'm going to copy exactly what I see. 1. Okay. Do I really have 4 carbons if I don't have the model and I'm just looking at the drawing? 1, 2, 3, 4. Okay. Now I'll challenge you. How many hydrogens does this molecule have? It's not butane anymore. It's not butane anymore. But it still has 4 carbons. C4H. How many hydrogens? Go ahead and pause. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It does fit the formula CnH2n plus 2. Check. This is an alkane. It's not butane. This is, well, I'm not going to tell you the name. I'll tell you that on a future video. This is still an alkane, though. Right? An alkane, the class of molecules called alkanes. We'll come back. This is considered branched. It's still an alkane even if it's branched, because it fits the formula, but for me, more importantly, it fits the definition that it's a hydrocarbon, only single bonds, or no rings. No rings. Okay. Are we ready for 5 carbons? Pentane. Okay. An odd number of carbons, so when you zigzag, you start at the bottom, you end at the bottom, because it's an odd number of carbons. Pentane. 6 carbons. Hexane. Okay. I'm not going to keep drawing these, but let me tell you 7 carbons. Heptane. Octane for 8. I said we're going up to 10, right? Nonane. And decane. Decane, 10 carbons. 1, okay, there's my starting point. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Double check. 10, good. C10. H. All single bonds, no rings. You would predict 22 hydrogens. 2 times 10 is 20, plus 2 is 22. And on your own, I'll let you count for yourself. If you didn't know that formula, okay, I'm trying to reduce the number of things you have to memorize. I normally don't care if you memorize the formula. What I care about is whether you can count the number of hydrogens from the line structure. 1, 2, 3, 4, 5, okay, etc. What about the condensed structure? You have at the end CH3. It's this last dot on the left. And we have 1, 2, 3, 4, 5, 6, 7, 8 carbons that have 2 hydrogens. So what you can do is you can do something like this. You nest the 2 within the parentheses, but you have, not 3, you have 8 of them. Oof. So right now, how many carbons do I have? I have these 8, and the 9th one is here. Decane is 10 carbons, so the very last carbon has 3 hydrogens, CH3. This is okay way. Well, this is the preferred way to draw the condensed structure. If you wanted to, you could also draw it like CH3, CH2, 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 etc. Okay, etc. Where are we? Okay. We talked about butane. Even if it's branched, the alkane will still follow this formula. We talked about counting hydrogens. We still have time. I'm trying to keep these videos under 30 minutes each. Why don't we introduce branched alkanes? Why don't we also call this Roman numeral number 1. Roman numeral 1. Unbranched alkanes. Okay, memorize those prefixes. Meth, eth, prop, etc. 2. Branched alkanes. And I'm trying to figure out if this is the best way to categorize them. Branched alkanes. And actually, we're going to call these simple. Yeah, simple branched. we're going to have later on more complex branches coming off of these alkanes. And we already actually saw an example. This is an unbranched alkane, and this is a branched alkane, the one on the right. Because if you shrink yourself down and you start on the very left, on the west, and you go towards the east, you'll come to a fork in the road, and you got to decide, well, if you're going to keep walking, or you go up, or you're going to go down. You reached a branched. This one you could walk from one end of the molecule to the next, to the other, without encountering any forks in the road. These are both alkanes. They don't get fooled by that. They're different. They have different names, but they're both alkanes. What is not an alkane? If I make those 4 carbons go into the ring, 1, 2, 3, 4. Okay. This is not an alkane. This is called a cycloalkane. Was I supposed to talk about cycloalkanes? Let me quickly talk about cycloalkanes, and then if we have time, we'll go to the simple branch alkanes. It's not technically an alkane because look at the formula. C4H. Everyone? I don't know the general formula for a cycloalkane. I'm just going to count. Okay? There is a formula, but I'd rather just count and be sure. 1, 2, 3, 4, 5, 6, 7, 8. If you want to do well in the class, you got to be that fast. You got to practice until you're that fast. These two, right? C4H. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. C4H10. Okay. Before we name this, okay, because this is not butane, this is butane. Let me name you the simple cycloalkanes. And I think this will, this is maybe a subcategory for the unbranched alkanes. Again, even though it is a cycloalkane. Alright, so enough about that. You can't have a ring with 1 carbon. You can't have a ring with 2 carbons. You could have a ring with 3 carbons. You're going to put cyclo at the beginning to indicate that it's a ring propane. The square, cyclobutane. Do you see the pattern? You just put cyclo at the beginning of propane, butane. Pent, like the pentagon. Cyclopentane. Hexagon, like a stop sign. I know, that's not a stop sign. A hexagon. Cyclohexane. I like to draw 7 carbon rings. I've been practicing for years. 1, 2, 3, 4, 5, 6, 7. Cycloheptane. Okay, I'm not going to write it out. Cycloheptane. Finally, we'll stop at the last one. Stop sign. Cyclooctane. At home, give the molecular formulas. So here's a little home, a reminder, question mark. What are the molecular formulas? Okay. For the last 4 or 5 minutes, let me give you some examples, but we're going to look at this more in depth in a different video. But I do want to introduce simple branched alkanes. Oh man. Paper got wet. Nice. Okay. Roman numeral 2. Branched alkanes. Simple branched alkanes. The first one is based off of butane. Okay. Well, I wouldn't even say it's based off of butane. It has the same molecular formula as butane. These are not identical, by the way. Not identical. Okay. You want to identify first the longest carbon chain as your parent. Longest carbon chain as what's going to be called the parent. And then you're going to, see that? You're going to identify any substituents. We have parents, and we have substituents. I suggest that you number your parent chain, circle your substituents. Okay. You're going to number, and you're going to, I like to use a dotted circle. Any carbon that's not part of the parent is a substituent, or part of the substituent. We're going to have very simple substituents at first. That's why I call these simple branched alkanes. Our longest carbon chain, we could count in several different directions. 1, 2, 3. 1, 2, 3. 1, 2, 3. So there are several candidates for the longest carbon chain. Many times it won't matter which one you choose, and you'll end up having the same name as your classmate who chose another longest carbon chain. But you got to make sure that you pick the longest carbon chain. I'm just going to make it simple, and I'm just going to start from the left like I read. 1, 2, 3. I know that there are 4 carbons, but that 4th carbon is not part of the longest carbon chain. And if you really want to get specific, it's the longest continuous. As you're walking along the chain, you have a choice, and I went to the right. Another person could have gone up, and they will still have a 3 carbon chain. This carbon doesn't have a number to it. That is my substituent, and look how I'm going to circle this carbon. Okay, I'm not going to be ambiguous. This is ambiguous. If you do something like this, if I ask you to circle the substituent in this case, and you give me something like this, okay. Can you see the difference? The difference is this person is ambiguous. Is that carbon in the middle part of the parent or part of the substituent? You can't double count a carbon. It either has to be either one or the other, either part of the parent or part of a substituent or the substituent. Okay, so don't do that. Don't circle it like this. You want to put your dotted circle, bisect the bond in the middle of the bond to avoid any confusion. Not for the grader, but even for yourself. Like, you might think this carbon is part of a substituent, a 2-carbon substituent. You have a 1-carbon substituent. This substituent is called methyl. And it's not methane because that is reserved for the parent. That is reserved for the parent. We'll go over more molecules like this, but for now, I will explain in the separate video why this is 2-methyl propane. That is the official name for this molecule. Okay. Using nomenclature developed by the organization IUPAC, International Union of, I'm going to look this up before the next video. I will definitely look it up. Alright, so that's your introduction to naming unbranched alkanes and our first branched alkane, and our introduction to line structures. For now, we're going to rely mainly on line structures to communicate what molecules that we're working with.